All right, thank you. For the next 40-something minutes, I'll be talking about just-in-time compilers for JavaScript, mainly how they work and what kind of bugs you can find there. We'll start with, let me turn this on. Yeah, we'll start with a short overview. How does a JavaScript engine look like? So these are kind of the main components you'll need to make a JavaScript engine. First, we have the parser that basically takes your JavaScript code as textual representation and converts it to bytecode, usually like custom bytecode for the engine. So it's also kind of a bytecode compiler if you want. Next, we have an interpreter and or a JIT compiler, which basically consumes this bytecode and somehow executes it, right? So the interpreter can just execute the code directly. The JIT compiler first converts it to machine code, then runs your machine code. So while this code runs, it interacts with what I call the runtime, which essentially defines various data structures like values, objects, and so on. And it provides a bunch of built-in functions, objects, etc. And finally, we have the garbage collector. So JavaScript is a garbage collected language, meaning the programmer doesn't need to take care of freeing memory, so the garbage collector does that. So with that, here's what we'll talk about today. We'll start with some introduction or some background on the runtime, how it works mainly. We'll talk about JavaScript values and objects. Then we'll talk about JIT compiler internals, how they work, how they convert JavaScript to machine code. Then we'll talk about a text surface, what kind of bugs you can find there and how to exploit them a bit. And finally, we'll talk about one specific bug in WebKit, which I used for Pwn2Own this year. All right, start with the runtime and actually start with JavaScript values. So JavaScript is what is called a dynamically typed language. That means that, for example, variables or properties, they can essentially change type. So if you look at these code snippets here, you see this variable A, it's first a number, then it's a string, it's an object. That's all fine. For the engine, that means that it has to store type information together with this value information. And then the challenge here is to do this efficiently. And usually the solution ends up being some clever hacks that manage to store both type and value information in 8 bytes. There's 2 of those clever hacks, basically. One is called non-boxing, and the other is pointer tagging. For this talk, we'll talk about pointer tagging just because it's a bit simpler. Actually, we'll use the schema from V8, the Chromium engine. So in V8, a JavaScript value is basically an 8-byte number or 8-byte value, assuming 64-bit architecture. Now, if the least significant bit, if that is cleared, if that is 0, then this thing is a number or a small integer, they call it. So that's what you see on the left here. You see the least significant bit is 0, and then the payload, the 32-bit payload, is stored in the upper 32 bits. So this value, if you see that in an engine in V8, represents the number hex 42. On the other hand, if the least significant bit, if that is set, then you have a pointer, and that's pointing to some object, and then at that location there will be more type information. So you can see here on the right side, that value has the 1-bit set, so it's pointing to some kind of object. All right. So speaking of objects, that's the next data structure we'll look at. So the question here is how to represent objects efficiently. For us, an object is basically just kind of a collection of key-value pairs, keys being strings and values being JavaScript values. So if you wanted to store that, maybe the first thing you could come up with is just make a hash map that maps strings to values. Yeah, that's quite simple, but it's not what happens. So in reality, in all of the major engines right now, what they do is essentially they separate property name information from value information. And then they have this object that I'll just call a shape for this talk. This shape object essentially stores the property names. So let's look at that. Again, this is the object we want to represent, so X and Y properties. And then instead of having this object store with a hash map mapping strings to values, instead we have the object which points to its shape. So that's a separate object. Now this shape essentially maps property names to integers. And these integers, they are being used as indices into basically a dynamically sized array of values associated with every object. Okay? So let's say you wanted to look up the property x on this object. What you would do is first go to the shape. Then you could see that property x is stored at slot 0. Then you go back to the object, go to the slots array, and then you find the value 41. So that's how it works. So you're probably wondering why are they doing that? What's the benefit here? Let me show you an example. So again, we have the same object, x and y properties. Now if you create another object that's similar in the sense that it also has x and y properties, now suddenly those two objects, they are able to share the same shape. So there's no redundancy essentially, right? So that's the main benefit here, that these shapes, they can be shared, so they can be used to conserve memory basically. And they are shared between similar objects essentially. So the next question is, well, what happens if you change one of those objects? So for example here, if you add a third property to the first object. Now, those two objects, they can't really share this shape anymore because the second object doesn't have this property. So in this case, well, we have to separate those shapes again. Now there's two. One has 3 properties, the other has 2. The one important property here is that shapes are essentially immutable. That's following from the fact that they are shared. So then next thing, if we were to add this third property also to the second object, then again they can share the shape. There's some clever mechanisms that make this work efficiently, but yeah, this is essentially how it works, or what happens. If you look at any of the major 4 engines right now and see how they implement objects, what you would find is essentially that all of them have a reference to this shape object, and that's called differently in all engines. So in Firefox, it's actually 2. It's called shape and the group object. In V8, it's called map. In WebKit, it's called structure. And in Edge, it's called type. But they all do the same thing. They are shared and immutable. That's the 2 important properties. And they fully describe the object. They tell you which properties it has, where they are stored, what prototype it has, etc. Then you have these property slots, and usually you have a few property slots stored inline, so a fixed number of inline property slots. And then you have an out-of-line, a pointer to an out-of-line property slots array that's dynamically sized, where all properties are stored that don't fit in the inline slots. So then the other thing you have is usually a buffer for element storage. That's just due to the fact that in JavaScript you can kind of use every object as an array, so they also have this array storage essentially. And then you might have additional type-specific fields. So for example, if you have a regular expression object or a typed array object, you would have more data fields in these objects. But these are the main ones, the first 4. All right, so the next thing we'll talk about is basically JIT compilers, how they work for JavaScript. So we do kind of a 10 to 15 minutes tutorial how to compile JavaScript. But first, let's start with some motivation. Why do we want JIT compilers? We already have those interpreters which can just run our code. So what's the benefit of just-in-time compilers? Well, it's probably quite obvious. It's code speed. If you have this optimizing JIT compiler, it's probably running much faster than interpreting your code. However, there's some drawbacks also. So one is that the startup time of an interpreter is probably much lower. So it can just start executing the code immediately after the bytecode compiler finishes, versus a JIT compiler, it has to do these expensive optimizations, etc. So it takes a lot longer to start executing code. Kind of the same with memory. The interpreters probably using less memory than the JIT compiler. As such, what all the major engines do right now is have essentially a multi-tier architecture where they start running code in the interpreter. Then they monitor how many times this function has been called. And at some point they determine, okay, this function has been called a lot of times. It's probably worth optimizing that. Then they put that through their JIT compiler, produces optimized code. And once that's done, they switch to the machine code. So this is how it works. All right, so let's talk about how to compile JavaScript. Here's a small function, JavaScript function, just adding two arguments together. Yeah, how would you compile this to machine code? This seems hard, right? It mainly seems hard because we have no idea about types of the parameters. So A and B, they could be numbers, but they could also be strings, they could be objects, whatever. We don't really know, and this makes it hard to produce machine code here. So the plus operator in JavaScript, it's quite complex. If you look at the specification, this is the pseudocode for adding something in JavaScript, right? And all these blue functions are essentially subroutines, so it's really complicated. And you wouldn't want to emit this as machine code all the time. So let's look at another example. Here's another function that just fetches a property from an object. Again, this seems hard to make machine code for this. Same reason, we don't know the type of O, and in particular, we don't know its shape. So we have no idea where this property is being stored. It could be anywhere. So what that means is essentially that the major challenge here of JIT compiling these languages is missing type information, right? So that's what we just saw. So let's just assume that for some reason we had type information. So maybe we had kind of a JavaScript dialect that is strictly typed, and it tells us that A and B are SMEs, so these small integers in the 8. Can we produce machine code now? Turns out we can. That's quite easy, actually. We know the in-memory representation of SMEs. It's these tag pointers again. We can just add them together in this representation, right? So there's a machine instruction you can use to add registers. So that's quite easy. There's one catch, because in JavaScript there's no integer overflow essentially. So the engine here has to do what is called a bailout. If this addition overflows, what it has to do is essentially go back to the interpreter, so that the bailout, it bails out to the interpreter, and that interpreter, what it would do in this case is convert the arguments to doubles and then do double addition, right? But this bailout mechanism is quite important. We'll see it a few more times. Right, so obviously, well, we don't have strictly typed language, so we don't have type information. What we have is, or what we can have, is type information from previous executions. So remember I said that right now, when you run JavaScript in an engine, it first runs it in the interpreter, and only after some time it goes to the JIT compiler. So by the time we want to compile, we do have type information from previous runs. So we can just keep track of all the types we see for every variable. So how does this help us? Well, what we can do is speculate that in the future we will see the same types. And this is really the main trick here, and this is where the name speculative JIT comes from. So let's look at an example. Again, here's our add function. And let's say we keep track of it while it runs in the interpreter. And this is what we see. It's always being called with SMEs as arguments, okay? So at this point, when we compile, we speculate that also in the future we will see SMEs as arguments for this function. So how does this help us, right? So now we have type speculations for all variables. What can we do now? The trick here is to use so-called speculation guards. And these are just kind of small pieces of machine code that ensure that our speculation still holds at runtime. So they come in different flavors. Here's two of them. On the right side, you see a SME guard. So that just makes sure that some variable is SME as we expected. So it's checking this least significant bit here. And if not, it bails out. Again, bailout mechanism. On the left side, you see a shape guard, which makes sure that some object has the expected shape. What it does is just fetch the shape pointer from the object compared to a constant. And this works because shapes are shared and immutable. So that's why they are, how this works. So let's look at an example again. Here's the other function, the function that fetches a property. Let's say we speculate that O will always be an object of a specific shape. And then this is what we could generate as machine code. So first we have to make sure that O is not a SME. So we need kind of the inverse SME guard that makes sure it's an object. Again, checking the least significant bit. Then we have shape guard that makes sure we have the expected shape. And then at that point, if both of these guards run through, we have type information. We know the shape of this object, and we can just directly load this property from the object. So in this case, maybe property B is stored in an inline slot, so we can just dereference the pointer basically. Yeah, what that means is that essentially these speculation guards, they give us type information back. So that's the main trick for dealing with missing type information. So let's look at kind of a typical JIT compiler pipeline. This is what you would see if you were to go through the code basically. So right now it always starts from bytecode plus value profiles. That's not necessarily like that. So V8 used to feed the abstract syntax tree in its JIT compiler, but right now all engines, they start from the bytecode. Then they convert this bytecode to their own custom intermediate language, which they do because, well, the bytecode isn't really there for optimizing, so they convert it to a different form that's better suited for optimizing the code later on. Then they do this typing or specializing where they apply those, or where they look at those value profiles, do the type speculations, insert type guards, and then they end up with this graph, or usually graph-based intermediate language, plus runtime guards, and at this point we basically have type information. Afterward, it kind of looks like a classic compiler for, well, like C++ or Java maybe. So they run a bunch of optimizers to produce better, faster code. They end up with this optimized intermediate language. Then they have to lower that to machine code. So that's called lowering, selecting machine instructions, allocating registers, and so on. And then, we end up with machine code. So let's sum this up. What we've seen is that major challenge of JIT compilers is missing type information. Solution is to first observe runtime behavior, keep track of types, then speculate that we'll see the same types in the future, guard these speculations with these runtime guards, and then basically optimize and emit machine code. If you want to take a look at this, there's a really cool tool from V8 developers. It's called Turbolizer. What it does is basically render their intermediate graph-based language in a nice web-based UI. So that's what I did here. I just kind of compiled this function foo in V8, took a look at this graph, and what you see here is essentially a data flow graph. So parameter 1, that's O, it flows into a check heap object node. That's making sure it's not a SME. If it is, then it bails out. Next, it flows into this check maps node. So that's making sure it's having the expected shape. So remember, shape is called map in V8. And after these two checks, it knows the exact type of the parameter. So it can just load this field from offset 24 in this case, right? Cool. So now we have kind of a basic idea of how these compilers work. So let's talk about attack surface. So here I made, this is my list of kind of bug categories that I want to talk about in this talk. The list is sorted from basically classic bugs that don't really have anything to do with JIT compilers to very specific bugs that you can only find there, right? So the first one is memory corruption in the compiler. That's kind of obvious because these compilers are written in C or C++ actually, so they can have all these standard bugs, right? Overflows, use after freeze, etc. So it's really not specific to JIT compilers at all, and we actually won't talk about them any further. The next two categories here are bugs in the lowering phase where it converts to machine code, so we'll talk about that a bit. If there's time at the end, I can show some example bugs of mine for these two categories. If not, then you can find them on the slides afterwards. So then the biggest part, the biggest category that I want to talk about is incorrect optimizations, so we'll spend a lot of time there. And then at the end, I'll talk about everything that I didn't talk about because not enough time. Just very briefly. You can also divide this like this. So basically, the memory corruption bugs, they would crash at compile time, right? Because the compiler itself has a memory corruption bug, versus all the others, they only crash at runtime, or they produce faulty conditions at runtime, right? So they are a bit more interesting, I think. So let's start with the first one. That's these Lowpass handlers. So if you look at basically this lowering code where they convert from their own intermediate language to machine code, it usually looks like this, where they just have one function for every operation or every instruction in their intermediate language, and this function is responsible for turning that operation into machine code. So here's one example. That's what it might look like. Usually then there's a few different cases So there's one case, or a few cases where they know the type information, and the type information is so that they can specialize, essentially. So it's kind of the fast pass. So let's say you wanted to compile an addition operation, and you knew that your incoming arguments are always SMEs. So in that case, you can just emit machine code as we saw it. But then there's the other case where maybe all you know is that the argument could be an object or could be a string or whatever. And in that case, you don't really want to emit this whole pseudocode that we looked at, right? That was kind of a big list. So what you would do is just kind of emit a call to a runtime function, to a C++ function that then implements this big plus operation here, right? So the takeaway here is essentially that this function that's being called, this Lowpass operation XYZ in this code here, that's just kind of a built-in function, like all the other built-ins in these engines. That's a function that's implemented in C++. It takes JavaScript values, does something, returns a JavaScript value. So you can just audit it like all those kind of classic JavaScript engine bugs, right? So then let's look at the other paths here. Let's say we can specialize because we know that the arguments are maybe quite favorable. They are only always integers maybe. So in this case, this is somewhat what you would see in these engines in the code. What they do is usually kind of allocate a register maybe for the results, then emit some machine code to perform the operation, in this case like an integer multiplication. Jump if overflow in this case is also required, and then they set the result, right? So yeah, it's really just a code generator that emits machine code. So yeah, what could go wrong with this? What could happen? Essentially, this isn't too different from the previous one, right? So the previous example was C++ code that's doing something. Now this is C++ code that produces machine code that then does something, right? So you could essentially have all the same bugs in code like this. One thing that happened a few times is missing integer overflow checks, right? So this is always a problem. You can do the same bugs with this kind of code. There's some other stuff. So for example, you see here it has to do register allocation. That might be tricky. So there have been some bugs with register allocation here that you wouldn't have in the C++ code. But really, it's kind of still the same kind of JavaScript engine bugs that you will find elsewhere. So let's now talk about optimization. So this is the biggest chapter that I want to talk about, incorrect optimizations. So what is an optimization first? It's basically a transformation of code that is not required for correctness, but improves speed, right? So here's a simple example. We have this function here, circumference, computes circumference of a circle. And in this case, the compiler could notice that this expression 2 times pi is actually constant. So it could just pre-compute that at compile time and insert that constant here and save a multiplication at runtime. So that's called constant folding. It's a very basic optimization. And there's a bunch of others. If you look at those compilers, they have a huge list of optimizations they do. Some of them are quite complex, quite dangerous. So if that goes wrong, that usually results in pretty nice bugs. And we will talk about 2 of those. So the first one is bounce check elimination, right? It sounds pretty dangerous already, so that's, it is, turns out. The other is redundancy elimination that we'll talk about later. So let's talk about bounce checking first. Here's some code. What it does is just a function that you give an index. It fetches that index from an array, from a global array. If you compile that in V8 and you again look at this code graph here, this is what you would see. Again, this data flow graph, so it has this parameter 1, the index. It flows into this check bounce node. And this makes sure that I is between 0 and 4095. If it's not, again, bailout. If it is, then okay, that's in bounds, so we can just index into this array. So that's all good, and we need this check here because I could be arbitrarily large. So let's say I added another statement here. In this case, what I'm doing is just ANDing the index with hex FFF. And in this case, the bounce check isn't really required, right? Because the output of this AND operation must be between 0 and hex FFF. So this is the goal of bounce check elimination, essentially figure out what bounce checks are redundant or aren't required. The idea is to perform what is called range analysis. So essentially track all the possible value ranges of integers in the intermediate code. And then if it can prove that an index will always be in bounds, so it knows the range of the index, it knows the range of the array length. So if the biggest index is always less than the least array length, then it can eliminate the bounds check. So we can kind of see that here. Again, this code graph for this piece of code. So what you see is that parameter 1, it flows into this bitwise AND. And the compiler at this point, it figured out that the output of this bitwise AND must always be between 0 and 4095. So later, when it lowers this code to machine code, it realizes that the check bounds node is actually not required because the input is already in that range. So it will just eliminate the bounds check at that point, basically. All right, so what could go wrong with this? Well, quite a few things. Basically, every time you have kind of a discrepancy between the value range as computed by the compiler and the actual value range, that's a bug for this bounds check elimination. So why would that happen? There's a few reasons. One is due to integer-related problems. So integers are hard. Yeah, we kind of all know this. Or there's signness issues, there's overflow problems. And this range analysis has to track integers, has to really do a lot on integers. So it might run into any of these standard integer-related problems. The other source of bugs is essentially incorrect emulation of this compiler intermediate language. So remember the previous slide where I had this bitwise AND? The compiler essentially had to emulate this bitwise AND to figure out that the result would always be between 0 and 4095. Now bitwise AND is simple, that's quite easy to emulate, but there's a few others that might be a bit more tricky. And that's a really cool bug I like from a good friend of mine, Steffen, found in V8, and that's what we'll look at now. So there's this function called string.lastIndexOf. You can call it on a string. What it does is you give it a search value and it tells you the last index where this search value occurs in the string. So you might be searching for a character or whatever. Now the V8 engine, what it tried to do is essentially inline this call to this function, and it would try to predict the output value of that call. So last index of, what it can return is essentially -1 in case the search value isn't found, or it gives you an index. So what they thought is that, well, the return value of this call, it must be an integer between -1 and the maximum length of a string -1, right? Because it's an index, so it's must be less than the length. Or so they thought, because if you look at the documentation, there's this one sentence that says that an empty string search value will match at any index between 0 and the length of the string. So you can see that here in this code snippet, there's a string of length 4. If I search for the last index of the string empty string, it actually gives me 4, right? What that means is that this range, this typer code here that tried to determine the output range is off by 1. So actually, this call can also return string.maxLength. So how can you exploit this? This is essentially the pseudocode that you would need. So you start with a string of maximum length in this function that's being compiled. Then you do last index of with an empty string. At that point, the compiler thinks the output will be between -1 and the maximum length -1, but it can actually be between -1 and maximum length. So then you add 1 just to get rid of the -1. So again, the compiler thinks it's between 0 and max length. It can actually be between 0 and max length plus 1. Then you use it for an index into an array of this max length plus 1 size. At that point, the compiler thinks, well, okay, the index is always in bounds. I can just eliminate the bounds check. Reality, we get out of bounds access. And if you play around with it, you can basically get arbitrary out of bounds access. So if you're interested, I encourage you to just read the report by Steffen. It contains a full RC exploit for this bug. There's a few more examples where this has happened. So there's some Firefox bugs from a few years ago. There's 2 blog posts by ZDI about similar bugs, and then Project Zero also found some of those. All right, so let's talk about the other optimization. This is redundancy elimination. First question is, well, what is redundancy in this case? So let's say we have this function that's fetching 2 properties, adding them together. If you compile this just like with the schema we've seen, you might end up with code like this, where it first does the SME guard, then the shape guard, then fetches the first property, and then it again does the SME guard, shape guard, fetches the second property. Well, in this case, obviously, the second set of guards is redundant, right? There's no way the shape can change or the thing can turn into an integer in between. So in this case, what we want is this code, right? The second set of guards removed. So how would you do this? Essentially, the idea is to determine duplicate guards on the same control flow path and then just keep the first one. Sounds quite simple. It's actually tricky because you also need to keep track of side effects. So what is a side effect? Well, essentially calling arbitrary JavaScript is a side effect. So let's look at this function here. This is essentially the previous one. Just now I'm doing a function call in between calling some JavaScript. Let's say we did our redundancy elimination, and this is what we came up with. First set of guards, then the call to this argument function here, and then no more guards and directly the property fetch. Is this correct? Well, here's one case where it's not. Let's say our callback, what it does is delete the property B. In this case, the shape has changed, right, as a result of a side effect. So this access here, it cannot be safe. We remove this property B. This can't be good. So in this case, we have to keep the shape guard, essentially, the second. So that's what you have to do. If you realize there's a potential side effect here, you have to keep the following shape guards. Right, so this requires the engine to essentially be able to precisely model all side effects of all the operations in its intermediate language. And this is hard. So JavaScript is full of these callbacks. They are everywhere. They've been a big source of bugs all for the last years, essentially. And they continue to be a source of bugs in this case here. So let's talk about exploitation. How could you exploit a bug like this? For that, we need to talk a bit about arrays in JavaScript. So let's just do this very quickly here. So arrays are kind of commonly used data structures, so the engine tries to optimize for them. Let's say we have an array that only stores doubles, like in this case here. In that case, the engine would realize, okay, this is only storing doubles, so it would try to store these values as actual doubles and not as JavaScript values, which are a bit more expensive because they use more memory. So if you look at the backing storage of this array in a debugger, maybe you would see that it just stores raw doubles. And this information is also stored in the shape. So here for this array, the shape tells us that it's storing unboxed doubles. So that brings up the question, well, what happens if we store something that's not a double in such an array? And well, what happens? So first, before that, we only have these unboxed doubles in our backing storage. Now we put an object there. So now the engine has to go ahead and basically convert all these doubles to JavaScript values and then insert this object here. So if you look at maybe the last element here in this array, you would see it's pointing somewhere, and that somewhere, if you look there, you will find this double value again. So yeah, you can already tell why the engine tries to optimize, because JavaScript values, if it stores them as JavaScript values, it will take 3 times as much memory as if it stores them unboxed. But okay, so how can we use this to exploit these redundancy problems? So this is kind of the pseudocode for such a bug where you have an unexpected callback somewhere in between your JIT code that you're compiling. And then essentially the exploit looks like this. So you first optimize your function to work on arrays with unboxed doubles. So in this case, this is this for loop here. It's always calling it with an unboxed double array. Then you call it again, and this time in this callback, you transition the array to now store objects. And then if the function, if this callback returns, the JIT code essentially still thinks that the array is storing unboxed doubles, but it's now storing pointers. So in this case, what it would do is basically fetch this pointer, treat it as a double and give it back to you. So you would get this weird looking double, which is essentially the address of this object in memory. So that's an info leak. So we get a type confusion. That's basically what we achieve here. This bug, we've seen it a few times. Again, ZDI has written a blog post about it. Project Zero also found some bugs. And then there's this my CV from WebKit, which I used for Prone to Own, and that's what we'll talk about now. Right, so this was JavaScript core, the WebKit engine. They also use a graph-based intermediate language. They also do this precise modeling of side effects because they want to do redundancy elimination. In their case, there's this class called abstract interpreter, which is responsible for doing just that. It's tracking all kinds of read writes to stack, heap, and so on. And it's making sure, it's tracking essentially side effects, right? If you look at this abstract interpreter, it's essentially a huge switch case statement that for every operation in the intermediate language knows what side effects it has. In case it has side effects like a call instruction, it's calling this global world function, which basically says that, well, this has side effects, throw away all type information and keep following shape guards, right? So if we look for some other code here, there's one operation that's called CreateThis. What it does is basically during construction, it allocates the objects that's being constructed. And if you look at this code in the abstract interpreter here, you can tell that it doesn't call global world. So it's assuming that this operation is in fact side effect free, right? Well, it turns out it's not, and that's exactly the bug I exploited. So CreateThis, it can actually call JavaScript. The reason is, well, very JavaScript specific. Essentially, when you construct an object, the engine has to fetch a property from the constructor. And fetching a property in JavaScript, that's something that you can intercept. For example, with a proxy. So proxy is just kind of a tool that you have in JavaScript to intercept all these standard operations on objects. So here's kind of my pseudocode. You have this function C, which is the constructor. Then I put a proxy around it that intercepts property loads, and then I'm calling it as a constructor. Now it's creating this object that it's constructing, and at that point it's running arbitrary JavaScript because I'm intercepting property loads. So that's really the unexpected callback here in our example. So let's look at what happens now. This is the function we want to optimize. The first thing it does is this graph building phase. This is how it would look like in the intermediate language. First to create this operation, then shapeguard, or it's actually called structure check in JavaScript core because shapes are called structures. Then it's loading the element and storing it on the object. Next thing, it does something called check hoisting, which is an optimization where it tries to move these structure checks as far up as it can. So it's actually duplicating the structure check and putting it as first thing in the function. And then it's doing redundancy elimination. And at this point, it's removing the second structure check because it's assuming that CreateThis is side effect free. So what we end up with is this operation which can have side effects, it can call JavaScript, and then there's an unguarded access to this array essentially. And this is exactly the condition we can exploit. So for this, we can just use the same trick that I showed previously with the array confusion stuff and confuse doubles and JavaScript values. From there, we get these two primitives, address of and fake object, that I already used 2 years ago for another exploit, basically. You can read up later if you're interested here. And from there, it's really easy, or it used to be really easy. It's basically fake a type array as you get arbitrary read write that way, and then you can just run shellcode, basically. So this is kind of the proof of concept for this bug. It's a bit more complicated, so I'm not going to go through all of this code right now. If you ran this on the vulnerable version, it would crash with 41414141 because that's this weird double value that you have at the bottom here. If you're interested, I will push my commented exploit to GitHub so you can take a look. And then we'll do a demo. Right, so what you will now see, that's basically my full pwn-to-own chain. So it has the WebKit RCE, which gets this code execution in the renderer. And that's exploiting this bug, but only this one. So this one is quite powerful. It allows us to bypass all mitigations. And then there's two more bugs. There's one logic bug in macOS that gets me out of the sandbox. And then there's another logic bug that I use to escalate from user to root and then root to kernel, because that's kind of a additional security boundary in macOS, I guess. Right, so let's see this in action. So there's a calculator popping up, mandatory calculator. And here we can see this is KXTed, so it's showing the list of loaded kernel modules. And this is my own kernel module that loaded into the kernel without a developer certificate, so it's not signed in any way. Right, so this is a full chain, goes from browsing to web page to kernel mode code execution in kind of just a few seconds, and it's super reliable because it's basically just logic bugs the whole way. All right, so that brings us to the end. Obviously, we haven't covered everything, so there's a lot more to these compilers. There's this bailout mechanism, which I only touched on. It's quite complex, actually, to just at some point in the function go back to the interpreter and continue executing code there. So there's some potential for bugs there. There's some other mechanisms like on-stack replacement, where basically the engine can also switch to the JIT code while running the function. So let's say you have a function that has a while loop that's running very long. At some point, the JIT compiler could compile the whole function and then just switch to the JIT code from one loop iteration to the next. So that's also quite a complex mechanism. There's register allocation, which we haven't talked about at all. Also inline caches. Inline caches is essentially kind of something in between the interpreter and the speculative and optimizing JIT. But I have some references on the next slide if you're on the two of the next slides where you can read up if you're interested. And of course, all of these are quite complex. There's potential for bugs there, so enjoy finding them, I guess. Cool. That brings us to the end. So here's my summary. What have we seen? Essentially, we saw that type speculation and runtime guards make up for missing type information due to dynamic typing. We've seen a lot of complex mechanisms, lots of optimizations, potential for bugs, right? Very complex code bases. We've also seen very powerful bugs, so it's not uncommon that one bug is really enough to bypass all mitigations in a super reliable manner and super quickly. And the whole thing is also, again, kind of this performance versus security trade-off. Right now, the engines, they all go for performance, right? They want to do these very complex optimization to produce as fast code as possible, which results in complex code, potential for security bugs, right? So nothing really new. And as I said, there's some further references, just a list of kind of interesting articles. The slides will be published so you can take a look. And with that, thanks for listening. Thank you.